My name is Al Schriesheim. I am the Director Emeritus of Argonne National Laboratory and the President of the Chicago Council on Science and Technology. The nature of nano, the subject of the discussion tonight, is presented in partnership with Argonne National Laboratory. It is the 88th program that C2ST, Chicago Council on Science and Technology, is putting on. Now, nano, as you, I'm sure, essentially know some more than others, is what goes on when materials become very small. Richard Feynman, very well-known physicist, had a saying which I'll paraphrase, and that is that more things than you know go on down into the world of the very small. And issues of materials, the advent of major facilities, the ability to see things that go on have enabled us to, A, prepare these very small materials, and B, take a look at what the properties of these materials are. I'm sure you've seen a number of potential applications in the paper. Today, we're particularly fortunate to have Amanda Petford Long here. Amanda is a scientist, material scientist at Argonne National Laboratory. The Chicagoland area is fortunate in that it has centers of excellence in material science, and Argonne in particular has a nano center that Amanda directs. We also have 3 of Amanda's postdocs here. Would they stand up if they're not packing up their stuff outside? Oh, here they are. Give them a hand. And we also have, I understand, 10 students from the Chicagoland Jewish High School. 3 students. There they are. Stand up. I'd love to see students here. The program tonight is one that you can also see on WTTW. Amanda was on WTTW last night being interviewed. Yes, I saw it. It was excellent, actually. So I think, oh no, I'd like to introduce Akeem. Adam Khan. Stand up. Adam Khan. Sorry for the mispronunciation. Adam Khan is an entrepreneur who is developing some aspects of nanotechnology that involve making microscale diamonds, and that technology is a technology that was actually initiated at Argonne National Laboratory. So I'm delighted to see you here. Amanda, it's yours.
Switch that off. So is this microphone? Yes, it is on. Right. Well, good evening, everybody. Thank you very much for coming out on this extremely cold evening. We greatly appreciate it. And I'd like to thank C2ST for this opportunity to tell you a little bit about nanoscience and nanotechnology. I'm going to focus, obviously, on a lot of the work that we do at Argonne, but I'd like to start by perhaps trying to put in perspective exactly what we mean by nanoscience and nanotechnology. And being British, I took the definition from the Oxford English Dictionary, because that's obviously going to be right, which it says that It's all right, I can hide behind the podium. So the branch of technology that deals with dimensions and tolerances of 1 to about 100 nanometers, and generally with the manipulation of individual atoms and molecules. So that's nanotechnology, and the manipulation and control is the important part. And how we get to nanotechnology is really through nanoscience. And nanoscience is exciting because, as Alan said, we're looking at materials at a very small scale, and I'll put this in perspective in a moment. But really the point is that they show new properties and new behavior that can be very unexpected. And it's not that gold, for example, if you cut it up and make it very small, behaves like a big piece of gold, but just on a small scale. It actually behaves differently. And it's that difference in behavior that we can exploit for nanotechnology. So to give you an idea of the length scales, there's a scale up here starting at 1 meter and going down to 1 nanometer. And if I put that pictorially, because I think it's much easier to understand, we have a child over here at about 1 meter. And down here we have DNA and a virus, a cell, a hair, human hair here in the middle. And we're interested in the behavior of materials down at this scale. So we go from a human being down to a hair, that's a factor of about 10,000, and a factor of probably about 10,000 more as we go down. And there's all sorts of clever things that you can do at the nanoscale and the micron scale. This is a race car that's actually been printed in 3 dimensions into silicon at the micron scale. Here's a little snowman that's sitting on the top of a scanning probe microscope tip. That's about 10 microns. And down here we've got IBM written at very, very low temperature with 35 xenon atoms. So each of those dots that you can see is an individual atom. And we can move those atoms around on the surface. They don't naturally spell out IBM, unfortunately. It'd be nice if they did. It would make our lives a lot easier, wouldn't it, Adam? But we can move those atoms on the surface, and we can control those atoms. And that control at the nanoscale, as I say, is really what allows us to use these materials for all these nanotechnology applications. So it's really small. You know, I go around saying to people, it's microns, it's huge, because I'm used to dealing with all these nanoscales, and I have to remember sometimes that it's all relative. If I talk to astronomers, they sneer at me. Universe is very big, but stuff I work on isn't. So also to put in perspective, do you use nanotechnology in everyday life? And of course the answer is you do. If you live in Chicago, I would hope that in the summer you're all using sunscreen. And of course what protects you in sunscreen are the nanoparticles. They could be titanium oxide or zinc oxide, but they're very, very small. And the fact that they're very small means that they alter the way that light interacts with the sunscreen. And so that's what stops the UV radiation reaching your skin. If you're an avid tennis player or indeed a golf player, then if you use the very lightweight rackets and golf clubs, they have carbon nanotubes in them. Carbon that's a single layer of atoms thick, it's rolled up to make a little tube. And that's what's put into the material in the tennis racket to make it light and very, very strong. Band-aids coated with silver nanoparticles, very small particles of silver. It's been known actually for thousands of years that silver is naturally antibacterial. And when you go to the stores these days, you'll find a lot of very fancy items that say they have silver in them because it's antibacterial. It is, in fact, antibacterial. So this was a very interesting use. The earliest use, of course, really of nanotechnology, although they didn't know it at the time, is stained glass. Because the colors in stained glass arise because the glass is mixed with nanoparticles. The red color up here on St. Cecilia's halo actually comes, this is from the cathedral in Oxford, Christchurch Cathedral. The red color in her halo comes because that glass is doped with gold. And we don't normally expect gold to be red, but when you make it into nanoparticles, it changes the wavelength of the light as it passes close to the nanoparticles. So that's the very earliest use. But of course, that's unintentional nanotechnology. And here are nanoparticles, quantum dots, now made of an alloy between cadmium and selenium, or cadmium and sulfur. These were made at the CNM, and when we shine light on them, you can see all the different and beautiful colours that they show. And the colours actually depend just on the size of the particles. And then you can use those particles now to make displays. Samsung is working on a way of making flexible displays using those nanoparticles. Same kind of particles here and here, really, but here it's sort of unintentional, just fortuitous, and down here we're learning to control the shape and size in order to get the colours that we want. So there are lots of challenges that we face, and how to predict the behaviour of these nanomaterials, how to make the nanomaterials. As Alan said again, we have to know how to make them. We have to be able to control that, the way of making them. And if you, I hope, talked to the postdocs earlier on, you'll have seen on their posters some very cool ways of making nanoparticles and nanomaterials, and also then of looking at their properties. I think understanding, I would say, in the science, and then if we can control through the understanding, we can go on to the nanotechnology. And then we also, of course, have to incorporate these nanomaterials into devices. I'll talk later about hard disk drive. The heads in there are nanomaterials, but you don't want to be walking around just with a little nanomaterial on its own. We have to understand what happens to that material when we put it in a larger device. And then, as I'm sure several of you are aware, safe use of nanomaterials. We have to consider the fact that these materials do, in fact, behave differently at the nanoscale. Are there safety implications? And that's something that's taken very seriously. So if we think about what's being done nationally, because there are so many potential applications of nanotechnology, it really is a key for the future. And I would say that the governments all around the world are investing billions of dollars in nanoscience. If we look in the USA, for example, to date about $3.7 billion. I mean, this is a ballpark figure. Obviously, it's increasing all the time. And part of that has come about through the National Nanotechnology Initiative, to which Argonne belongs. And participants of that would include national funding agencies such as the Department of Energy, universities, national labs, and industry. And if we think about what the Department of Energy specifically is doing, they fund a lot of the work at Argonne National Lab and indeed set up the labs. One thing that they've done is to set up nanoscale science research centres, NSRCs, and there are 5 of them across the country. And one of them here in Chicago, the Centre for Nanoscale Materials, is where I work. And these were a really, I would say, inspirational idea on the part of the Department of Energy, because they're user facilities. There are other user facilities that the Department of Energy runs. And by user facility, basically anybody across the world, any of you. We have high school students. I'd encourage you guys to apply if you want, from IMSA, who come as users. Write short proposals to say what science they want to do, and then they can come and work with our scientists and use all the equipment that we have available. And it's free if it's non-proprietary. So if it's publishable in journals. But the inspirational bit about setting up the nano centres was that in addition to being user facilities, our staff have to spend 50% of their time doing their own research. So we have a very strong internal program. And so some of the work I'm going to show you are from our staff's own research, and some of it is from the users. I created this schematic recently for a review of our centre that we have, and I like the use of the cogs because really it does say to me that if you're going to do nanoscience and leading on to nanotechnology, you need the interaction of a lot of people and a lot of different ideas. We have people at the CNM who come from physics, from material science, from chemistry, from biology, from engineering, from a lot of different fields, and they're all working together. I was talking earlier with some people. There are language differences, I have to say, and we have to overcome that. And these groups, our scientists work in these groups, and then all of those groups work with the user facility, and we work very much together. And that is a very important part, I think, of being able to face and understand and address some of these challenges in nanoscience. And just very quickly, we have a user community that comes from 38 of the states and more internationally. We're trying to build our industrial users, and Adam, who's going to speak to you later from Nanotechnology, is one of our industrial users, because it's really important that we make ourselves accessible to anyone across the country and indeed across the world who wants to come and work with us and who can benefit from the kind of activities that we do at CNM. We have a lot of very cool toys to play with, I have to say. It's very exciting. It's a very exciting place to work. Argonne is a very exciting place to work. We're very fortunate. You know, on my days when I'm dealing with the paperwork and it's not quite so much fun, I just go and look at the labs and I look at the really exciting things that we have out there. But we can have lots of very shiny pieces of stainless steel. I'm not going to go through all the details. But without the people, this would be nothing. And it's the people, it's the staff and the postdocs who really make the place such a vibrant environment. And you know, some of this work is my own, but very, very little of it. And I'm very grateful to the people who've all been very prepared to share the really fascinating things that they do. So at CNM, we put our research under energy and information transduction. Transduction is an interesting word because what it really means is that you're taking one form of energy and transforming it, transducing it into another form of energy. And that's something that we do. It could be information. We could have an electron, a charge, an electrical signal coming in, and what goes out is light. Or we could have light coming in, what goes out is charge. We could take heat and do something else with it. But this is the idea that we can use the nanomaterials to transform between different types of energy and also use it as a way of moving information around. And broadly, we make stuff, we look at stuff, and we control stuff. And those things all have to work together. If we can't, somebody, this is a theoretical image here, but actually goes with some experiment we're doing. You know, you can devise something in a computer, but you have then to be able to make it. You have to be able to look at it and understand it, and you have to be able to control it. And we want to do all of those. So I've picked 6 examples out of the, I think it's 6, out of the work that we do that I want to share with you to give you just some flavor for the sort of things we do. And the first of this is related to catalysis. So catalysis is a way of either speeding up a chemical reaction or indeed controlling which chemical reaction you want to happen. In this case, we start with propane, these lovely cylinders that you lug home from Home Depot when you want to fire up your barbecue. But this is actually the starting material for polypropylene rope, polypropylene carpet, and that lovely pink stuff that they slosh all over aeroplanes, polypropylene glycol, when they de-ice. Propane, if left to its own devices, would actually break down probably to carbon dioxide or to carbon monoxide and other byproducts. We don't want either of those things to happen. And how we can control and force this reaction to happen to propylene feedstock, which is what goes into making all these products, is through catalysis. And one of the pieces of research done at the CNM was to look at the difference between having a propane molecule up here landing on a flat surface or on a nanoparticle. And before I run the video, I'll just show you what these curves show here are the energy surfaces. It's sort of, you can imagine you have to go, the molecule lands and then there's some energy that it has to use to transform into something different. Every time it uses energy, it has to go up a hill. Then it falls back down again and wiggles along like this. There are lots of different stages. But if you look at the difference between what happens on these 2 stages, and this did work when I tried it earlier. Come on, there we go. So these are simulations done at Argonne using our supercomputer, not in the CNM, but at Argonne, the Blue Gene P. And so these are simulations of 1,000 metal atoms. I look at this because I'm an experimentalist and go, well, that's not very many. And they look completely horrified and go, this is huge. We used to only be able to do 1 atom. And so what you're seeing is here, that you can tracing here now across this energy landscape. So you see this thing got stuck here on the flat surface. That's the blue curve, because it jumped up over this mountain and then it kind of got stuck. Whereas here's a little hydrogen atom that's coming off. And in a minute, the molecule's going to leave again, and now it's changed into something different. And the trick here, that the really cool thing with the simulations, which were then later shown by experiment, was that by going to this very small cluster, there's maybe only 4 atoms there, could be silver, platinum, palladium. You take away this large mountain that the reaction has to overcome, and you just reduce it to these nice little rolling hills here. And why that is important is shown on this slide. This is the total US energy uses, all of the energy that the whole of the US uses in terawatts. And that pie slice here is what's used currently to make ethylene and propylene. It's a small slice, but it's a heck of a lot of energy. And so if we can find some way of using that catalytic process to reduce the amount of energy, that's something that we should certainly be working on at the Department of Energy lab. So I now wanted to come on to some examples of what I've called functional materials and devices. And the first of these is read heads for hard disk drives. And this is the photograph of one of Seagate's micro drives. So there's a pencil in the background, and there's the disk, and there's the head that moves across the disk. And if we zoom in and look at the head, actually you're really neatly arranged here because you're arranged on arcs, and the bits of information on a disk are arranged on rings going around the disk. So you can all be bits of information on different tracks on the disk. I'm not sure what you all say, but I'd have to spend some time working it out. But if you all looked up, you're the disk and you're moving, the head's moving over the top of you. If you looked up at the bottom surface of that head that's moving over you, this is what you'd see. Part of that does the writing and part of it does the reading. And I'm not going to go into it in great deal to detail, but there's something in here that we can't even see, so we've blown it up here. 170 nanometers across is the read head. It's an incredibly complicated structure. It has all these different layers in it. Cobalt, iron, boron, alloy, cobalt with iron, magnesium oxide here. And actually the whole way that this works is the signal across this layer here. And this is a high-resolution transmission electron microscope image of that structure. So you can see all the atoms in there. And it turns out that a very important thing to control is actually how these layers behave and what happens when you heat them up, which is one thing you have to do to make the structure. And what we were looking at, and in this case, this is actually a Seagate head, but we were looking at this with a company in Japan, and Canon and Elva, that make the big pieces of apparatus that are used to grow these structures. If you look at here, the platinum manganese, then there's 2 layers, then ruthenium, then 2 magnetic layers, magnesium oxide, 2 magnetic layers. That's a very complicated structure. Why would they even bother with that? Why not just use 1 magnetic layer in each case? And so we went in with, in my research group, with something called atom probe tomography, which actually allows us in 3 dimensions to map out where the atoms are in the material. And if we look at one of these structures where we've only got 1 magnetic layer, I do apologize, I forgot to give you one rather vital piece of information, which is that what we're going to concentrate on is these 2 layers up here. If we replace those 2 layers by 1 layer, which was the original old structure, concentrate on the boron atoms, you can see here there are lots of boron atoms, and in here there are not very many boron atoms. So as we go across that layer laterally, we've got variations, which means it doesn't really work very well as a device. Put 2 layers in together, one underneath the other, and now across the structure, it's very much more uniform. The green is the iron atoms, so you can see the iron atoms, and the boron is just sort of dotted around, but it's very much more uniform, and because it's uniform, it works really well. And so basically, by being able to go in and image the nature and the position of the atoms within those layers, we could really say something about the device behavior and tell the companies about the device behavior. And why that's important, what I'm showing here is year against gigabits per square inch. And this is a number you should all be very interested in, because this is how many bits of information per square inch on your disk you can store. And if you think old computers, you know, took up an entire room and they stored like a tiny bit of information. Now we're all waltzing around with more computing power in our cell phones, probably. This is a very important graph because it shows how that density has increased with year. And really, I would say a large proportion of those increases, not all of them, because some are in actual how you program the disks, but a lot of those improvements in density, in areal density, have come about because of nanotechnology and because of understanding how those materials behave and being able to make them better. So batteries is a big area of research at Argonne across all length scales at CNN. Because we're a nano centre, we focus on nanostructured batteries. And if you look at today, all the sort of state of the art for energy storage, here are some cool toys that you might want to have. I particularly like to have an electric motorcycle, but they're very expensive, turns out. This is sort of how batteries behave. And at the moment, we're down sort of at this corner. Where we'd really like to be is up here. Because if we were up here, we would have batteries that lasted a long time, that worked very well, that charged quickly, that would allow, you know, us to have a car and go 300, 400 miles on a single charge. So we want to be in that upper corner. And there are all sorts of problems with batteries, and one of them is related to the fact that when you cycle batteries, they get worse. You know, eventually you have to throw them away. Now, some very interesting research is being done actually currently ongoing at Argonne, and that's to use titanium dioxide nanotubes. And I've called it a mat because literally, if you think of something like a doormat, those rather bristly sort of coarse doormats where you've got lots of fibers standing up on a flat surface, that's what the anode of the battery looks like. And each of those fibers is a very small hollow tube of titanium oxide, and it's amorphous. So all the atoms are just randomly arranged. They're not in any ordered crystal structure. And what we looked at, I suppose the movie's supposed to keep running, but I think it's stopped. I'll see if I can run that again. What we found was that as we charged the batteries and discharged them, they got better. The question was why? And so one of our theorists did some calculations, and this is a simulation here where he's looking at what happens when you take this titanium oxide and put lithium into it. This is a lithium battery. And it starts out very random, and then I hope you can see that we're starting to generate these lines of atoms. You're starting to generate a crystal structure. And by the time it's been fully charged, it's fully crystalline. It's a perfect lithium titanium oxide crystal structure. And this has it charges very fast and has a very high capacity. So this was a really, really nice thing that was shown by experiment first, but we didn't really understand why, but then by theory we could put that together with the experiment and understand it. And why that's important is because what we've been able to do is now to add this data point over here, which is getting us up towards that top right-hand corner, which is where we want to be. Now, of course, the other thing at the nanoscale is everything's very close together. It's very small distances. And actually, another thing I should have said with this battery is that it's very efficient. And that's because in a battery, you generate an electron and a hole. A hole is a positively charged electron. They travel in opposite directions, and that what is eventually is going to give you the voltage across the battery, which is what we're going to use. And if that electron and hole have to travel long distances, they knock into atoms and they get scattered and they stop moving. If you make the distances very small that those electrons have to travel, there aren't actually very many atoms they could hit on the way. And so it becomes much more efficient, and that's really another very good reason for going to nano. And we're looking at other materials systems I'm not going to talk about now. So, again, we're just trying to think of ways that we can improve the batteries. Solar cells are very important, and the reason they're important is because if you look at the total amount of sunlight striking the Earth, and I have to say, some days in Chicago it doesn't look as though there's any sunlight striking the Earth, but today was beautiful. It was lovely outside, a lot of sunlight. It's cold, but there's a lot of sunlight. the amount of power that's generated is 96,000 terawatts. That's just such a big number, I can't even really think about it, to be totally honest. But what you could compare that with is the projected global energy demand in 2050, which is a mere 30 terawatts. So we have so much energy that's there in the sun that we could use. And of course, there's all sorts of issues with efficiency in solar cells, but there is that just amazing source of energy, and we should be doing a lot more than we do currently to try and harness that energy, because there's just so much available to us. And one of the things that, if you think about solar cells, there are really three different types of material systems that they're based on. These are commercial systems based on silicon, they're based on cadmium telluride, or they're based on something called SIGS, which is copper, indium, gallium selenide. Silicon solar cells, silicon's very, very plentiful. Sand is silicon oxide, but it's a large energy investment. Cadmium telluride, well, cadmium and tellurium are unfortunately both toxic, and also tellurium is very rare. I mean, you don't have to worry about the cadmium telluride, it's encapsulated, but it's still, we'd like to be getting away from processing those types of materials. And for SIGs, gallium and indium are very rare. And so none of these are really ultimately what we'd like to go towards. But there is an alternative, and the alternative is to use organic materials. And you can make organic photovoltaic materials. Photovoltaic simply means you take light in and generate a voltage with it. And these are ideal for solar cells. You can produce very high throughput. They're very low cost. They're mechanically flexible. Effectively, you can sort of paint this stuff on some flexible substrate, as you can see here. They're very lightweight. You can tune the color by tuning the chemicals that you use. And you have a low energy investment. At their best, they're nanoscale. I said at the beginning, the level of atoms and molecules. These are organic molecules that we're talking about. But they can be, and the layers are nanoscale in thickness, sort of 100 nanometers or so. And what we've been doing at CNM is to try and look at the internal structure of these organic photovoltaics, because you have to take a number of different polymer materials and put them together. And when you start doing that, they kind of self-arrange in a very complicated way. And if you don't understand how they've self-arranged, you're not going to be able to improve it, which you might want to do. But also, if you can't understand it, well, that's not really ideal. It's some kind of black box you're selling to people, and you don't really know how it behaves. And so what we could do was to go in, this is a schematic here of one type of material here, another type of material here. This at the sort of largest scale was what we thought the structure looked like. But in fact, when you go and delve inside it, you find there are little sort of domains, we call them, of regions of these molecules which are actually quite separate. And that is good because, again, here's this positive and negative charge that I was talking about, and you want to separate them. You want the positive one to go this way, negative one to go that way. They've got very short distances to travel. And one of the materials, actually, that we've been working on is PTB7, and this is the molecular structure of PTB7. And this is a molecule that was developed at the University of Chicago. And actually, if you put that in a solar cell with fullerenes, which are carbon C60, buckyball is a fullerene, currently holds the record for a polymer solar cell. So we work with users from the University of Chicago to understand these structures. Another way that we can capture sunlight is to try and mimic what plants do really rather well, and that's artificial photosynthesis. They do natural photosynthesis. We try and mimic it with artificial photosynthesis. So I'd just like to tell you a little bit about some work we're doing on that. And I'm sure you all know leaves are green because of chlorophyll. And this is an image of a natural photosynthetic bacterium. And they all contain these chlorophyll-based light harvesting complexes. And what these complexes do is they take in sunlight, yellow light over here, and then they deliver energy in some form to a reaction center, which is where the chemical reaction happens. And so this just sort of keeps running. So what you can see, here's the red charges that are generated, and you can see them running around those chlorophyll molecules when the light comes in. And then they all go into the reaction center, and that's where the photocatalytic reactions happen that power the bacteria. And what's very interesting about this, actually, is that what nature has learned to do over a very long period of time is not only to generate those charges, but also to have them move in a directional way. And that's actually quite difficult for us to do. It's really quite difficult. We can generate the charges, but then they just go off in all random directions that they happen to choose. So nature has learnt to do this in a directional manner, and so what we've been working on is a way of doing the same thing directionally. And this is based on using some artificial structures called metal organic frameworks, in this case produced in Joe Hupp's group at Northwestern University. And this is through an interaction, then the optical properties have been measured at the CNN. So there are molecules called porphyrins, which are analogues of chlorophyll. And as we'll go on to see, they're sort of, roughly speaking, they're very kind of flat molecules. You can think of being a bit like playing card shaped. And so you can arrange these in these nice arrays, link them together with organic linkers, and you've got metal ions in there as well. You know, and you can create chunks of the stuff, say 500 microns. To me, that's huge, but it works very well. And they're compatible with other photoelectrode materials. And that's important because remember I said at the beginning, we can make any wonderful materials we like, but if we can't sort of have those so that they're incorporated into devices, then we can't use them. And the way this works is that when we shine light, and that's the little lightning symbol that comes in here, we shine light in, and it generates this electron and hole, and this charge travels through the molecules. And what you'll see is that they move from flat face to fat face of the porphyrin. So by controlling the separation of those porphyrin molecules, we can actually control the direction in which the charges will travel, because they're only going to travel from flat face to flat face. They're not going to travel sideways. How do we know they're doing that? Well, we know they're doing that because every so often they give out some light. And this one here, it gives out that little red squiggle. And the red squiggle is some light that we can measure. The other thing that we can do is we can actually even measure how many of those molecules the charge is moving through. And we can measure that by putting in these orange molecules here, which absorb the charge. They suck it up, and so we can see how far the charge has moved. And so this is really a way of being able to produce this directional flow of charge. And then you could imagine putting this into some structure like a fuel cell, where the electrons go one way, the positive charges go the other way, and now you've got a way of using what's effectively the same mechanism, so artificial photosynthesis, as is used by chlorophyll. So the last example I wanted to come on to is not related in any way to energy, really, but I just think it's a really cool example. We are co-located at Argonne next to the Centre for Nanoscale Materials is co-located next to the Advanced Photon Source, which is our X-ray synchrotron. It's a hard X-ray synchrotron, so very high energy X-rays, and it's the brightest X-ray source in the Western Hemisphere. And they have about 60 beam lines around a ring where the X-rays are generated. And so you can have lots and lots of experiments going on at the same time. And there's all sorts of very fascinating things which are way beyond the scope of what I'm going to talk about today that go on at the Advanced Photon Source. But one of the end stations, one of the beam lines, is the hard X-ray Nanoprobe, and that's part of the Centre for Nanoscale Materials. And what we can do there is we can take the X-ray beam, we can focus it down to a very, very small spot, and then we can use that to go in and probe either the structure or the chemistry of a material. And currently it's the Nanoprobe that has we can make the smallest spot basically in the world for hard X-rays. Some very clever people work with us to design the instrument, and now there's a lot of science that's coming out. And of course, we spend a lot of the time looking at batteries or devices or geomaterials. But last year, the Art Institute, Francesca Casadio came to us and said, could we look at paint? And we wanted to look at paint because basically there's interest for particular paintings of knowing whether Picasso used artist paint or whether he used house paint. And this is a picture over here of the Ripollin factory in Paris. And one of the paints that they produced, it's a white paint. The focus was on white paint containing zinc oxide. If you look about and so we wanted to go in and look at that at the nanoscale. And pretty much the hard X-ray nanoprobe is the only way you could do this. Paint, it turns out, is a very complex material, whether it's artist paint or whether something you buy in Home Depot and paint on your walls very laboriously. It's extremely complicated. It has a lot of ingredients in it. At the macroscopic scale, here's a tube of paint. At the microscopic scale, the paint contains flakes, and that's actually what gives the color. And what we wanted to look at were the zinc oxide nanoparticles, which are what are the pigment in white paint. But we wanted to look at them at the nanoscale. And we wanted to look at them at the nanoscale because those paint flakes contain a very special signature. They're all zinc oxide, but they have other elements in there as well. They might have iron, they might have calcium, they might have barium, different elements. And actually there's a sort of signature that you can look at the nanoscale for these different types of paints. And if you look at that here for the Ripollin house paint and artist's paint, and in case you're wondering where on earth we got hold of paint from the 1800s, the Art Institute, it's really cool. They actually have a sort of library, really, of paints that they've collected from all over the world, from all different eras, so they can do this comparison of paints with paints in the paintings that they have. So here's Ripollin, here's an artist's paint, here's the zinc oxide, so we're mapping the zinc. We can look at the distribution of these elements in the material. And then here's iron, titanium, lead, here's iron again, here's titanium again. And if you're an expert and you know what you're looking for here, what you can see is that the distribution of lead, here's lead, is different. In the artist paints, the lead's in quite large blobs. In the Ripollin paint, it's much more finely distributed. And so you can just go in, we can look at these images and we can say, well, okay, Ripollin paint looks like this, artist paint looks like that. And then what we were lucky enough to be able to get hold of was a teeny tiny flake of paint from one of Picasso's paintings that Francesca had got hold of. And we could look at the zinc, calcium in this case, barium and iron, and look at the distribution of those paints, of those elements within that paint and try and decide which it best matched. And in fact, if you go in and look at that, it really best matches the Ripollin paint. And so that's really interesting because, you know, if you go and look at these, here's Volker Rose, who actually did the microscopy at the CNM, and here's Francesca from the Art Institute, and here's one of the Picasso's paintings that the Art Institute has. But the result is Picasso used common house paints in some of his artwork. Which is, to me, actually very fascinating. It was available in larger quantities, the texture's somewhat different, so he could by using these paints, he could do very different type of artwork. And actually, since we've done this work at CNM, we've done a lot of other work on daguerreotypes and other works of art, because it's turning out that this is really one of the only ways that you can go in at that very fine scale and just see what's happening. So those are the examples that I wanted to share with you. And what I sort of in summary would like to say, I suppose, you know, in medieval times, nanoparticles in stained glass, it was nanotechnology by chance. I don't think anybody in medieval times would have been able to tell you that they'd got gold particles of a few atoms in size. And it's absolutely fascinating to me, I have to say, that they somehow discovered this and were able to use it. Now we can do nanotechnology by design. Just as well, this is nearly my last slide because the pointer's about to run out. So now we can do nanotechnology by design. We know how to make those individual building blocks. Nanotechnology for the future is really how we put those different building blocks together and how we get that complexity. Maybe I want to put a magnetic particle structure together with an optical one, together with one that responds to light or one that responds to sound, whatever it might be. Probably not sound because the wavelength's a bit too long. But by putting those different materials together, we can get complexity and function that you could just have never dreamed of because it's not out there in nature. And so that's what we're striving to do. We're striving to tame nanoparticles and bend them to our will and use them in ways that I think are very, very exciting. And I wanted, this is my very last slide, just to put some acknowledgements up here. I'm very grateful to my colleagues at the CNM for contributing slides. It's always very cool to look at the research that they do. I'm also very grateful to our colleagues outside Argonne who come and use the CNM as users and who collaborate with us. I'm grateful to DOE, to the Department of Energy, who provide a lot of money. And that makes it possible for us to do the wonderful research that we have the opportunity to do. And particularly to the Centre for Nanoscale Materials, where I am, the Electron Microscopy Centre, and the Advanced Photon Stalls. And I'll stop there. Thank you.
Good evening. Thank you very much. I'm Adam Kahn, founder and CEO of Acon Technologies. And we are a fabulous semiconductor company specializing in energy-efficient diamond-based semiconductor for electronics application. Clicker here. Nope, this is just the pointer. I touched the screen here. Sorry. Oh, great. Thank you very much. Technologists that can't work the slideshow here. So I really love speaking about the science that we work on because it's quite fascinating. We get to talk about two very interesting things, both nanoscience and semiconductor applications, which both are largely impactful on our day-to-day lives and going forward will be even more so. So semiconductors are ubiquitous in application. They're found everywhere in our day-to-day lives, surprisingly so, everything from automobiles to aeroplanes, washers, dryers, or healthcare, in addition to what we traditionally think of when we talk about technology, computers, tablets, and cell phones. And semiconductors have many useful properties, but what we're going to focus on for this talk is the ability to amplify, switch, or convert energy inputs, right? Taking very high levels of voltage and switching them down, switching frequencies from megahertz to gigahertz to allow things like cell phones to work. And semiconductors actually are so named because we can change the conductivity through the addition of foreign atoms, right? Through a process called doping. And from an economic standpoint, semiconductor industry is actually rather quite large, presently valued at about $340 billion worldwide. But when we incorporate and include all of the jobs and services that are included in there, and if we add in things like electronic systems, approximately 1/3 of the global GDP is driven by the semiconductor industry. And it's the largest component of the US manufacturing, where today about 95% of semiconductor devices are based on silicon. And I emphasize the today part because in technology, it's not really the concepts that are changing, but rather the capabilities. And a recent story surfaced, and I thought this is rather interesting. The concept for the Apple iPad, Steve Jobs actually innovated it in 1983, where he said, what we want to do is we want to put an incredibly great computer that you can learn to use, carry around with you, and learn to use in about 20 minutes. But what we want to do, we want to do it with a radio link so that you don't have to hook it up to anything, and you're constantly in communication with all of these larger databases and other components and computers. So why didn't we have the iPad in 1984? Because we didn't have wireless interlinking of digital devices. We didn't have Wi-Fi. We didn't have Bluetooth. So more close to semiconductors, in World War I, we actually used switching accomplished via vacuum tubes, these large systems that enabled radio communication intercontinentally. Shortly after World War II, though, we had transistors, which could accomplish that same function, where the concept is the same, but the capability has now changed. So in the beginning, it wasn't a silicon-based industry. It was actually germanium-based, because silicon, even though it's derived from sand, was believed to be too expensive to commercialize. Very, very high costs associated with purifying silicon enough to make it electronics grade, and very high processing temperatures, about 1,000 degrees C. But early on, in the devices made from germanium, a very interesting phenomenon happened where if you were in your car and you wanted to listen to the radio and you left your car parked in the sun and you came back to it, the radio no longer worked. And that's because semiconductors are in between a metal and an insulator. If we think a metal is always conducting, we can say it's always on. An insulator is very tough to put conduction through or put electrons through, so it's generally off. Semiconductors can switch, and when we dope these materials, we're able to make it better electronically conducting. So there was a strong motivation early on to replace these germanium-based transistors with silicon ones. And what we notice is that germanium, silicon, and carbon all arrange their atoms in a lattice structure known as the diamond lattice. And in the 60s, there was an abrupt shift away from germanium to silicon over the duration of just a few years. And that's because silicon has superior electronic properties as compared to germanium, largely due to smaller interatomic spacing. Right? The atoms are more closely arranged in silicon than they are in germanium. And that allows it to be a much larger gap as compared to germanium, right? So it had to take much more thermal energy to be able to switch the electrons out of the vacuum, out of the ground state and into the vacuum ambient. So we can see that the silicon gap size is almost twice that of germanium. And if we look to diamond, we see it's nearly 5 times that. So this allowed a very rapid pace of progression in technology, where nearly every 2 years, the amount of transistors in a microprocessor was virtually doubled and accomplished in a much smaller feature size. Now, that sounds like a very neat thing that, wow, chips are getting smaller and smaller, but it's out of necessity, not out of convenience. They didn't build it because they could, they built it because they had to. And why is that? Well, we see if we start in the beginning, the average microprocessor had about 2,300 transistors on it, or the size of your average music hall. If we fast forward about 15 years, we're now accommodating the seating capacity of Soldier Field in that same area of that music hall. If we fast forward another 15 to 20 years, we're now accommodating the city size of Tokyo in that same music hall, where today we're putting the size of population of China in that same music hall. So this is actually a large problem, not only because some point in the future we're going to reach transistors that are the same size of silicon, but more specifically because power and thermal management is a major issue in these electronics. And so I'm sure we've all noticed or heard about that Tesla's catching fire due to thermal runaway, or iPad Airs exploding in the iPad store. But more specifically, if we're using our cell phones for very short durations, we notice they start to get hot. And why is that? Because previously a cell phone used to be just a cell phone. Now we have increased levels of functionality, where a cell phone is also a camera. It's also a camcorder. It has GPS technology in it. And that's a major problem because we're at a point now where silicon is reaching its physical limitations, and it's noticeable. And the present ways that we cool these devices are dramatically inefficient. Right? There's essentially 2 different ways we cool it. Either convection-based cooling elements, which are bulky and inefficient, or we use rather expensive packaging materials where we combine plastics with these metals and very thin profiles, but with very marginal increases in the thermal dissipation. And so this is actually a much larger issue because, for example, in data and computing centers, of the 120 billion kilowatt hours that are consumed worldwide by these data centers, approximately 50% of that goes straight to cooling. And actually, it gets much worse because these are not environmentally friendly methods that we're using for cooling. Actually, electronics waste is another major issue in technology, where each year over 50 million tons of electronic waste is generated, and it's shipped overseas without any thought, where only 15% of it gets recycled. Mostly it gets incinerated, where these toxic chemicals and greenhouse gases are being released into the ambient environment. And unlike us, these pollutants don't require passports for travel, right? They go up into the jet stream, they're carried around the world. So as the developing world increases their technological use, this is going to get more and more problematic. But again, it's not really the concepts that are changing, it's the capabilities. So one thing that, or one particular material that's been looked at is diamond as a potential successor technology. And that's because diamond handles heat much better than silicon, about 22 times more efficiently by thermal conductivity, and about 5 times that of copper. But more importantly, and more specifically for power electronics use, diamond actually has a superior capability because we can put tremendous amounts of power in much smaller area. We can drive it at much higher frequencies. And if we think about in terms of the material, just to isolate a specific amount of voltage, it's about 50 times smaller than silicon. So we're using less material, which is more power efficient and more thermally efficient. And I really love working at Argonne because Argonne has long been at the center at diamond in the CVD boom. But again, it's not a new concept. Diamond's actually, or the concept of synthetic diamond, has actually been around since 1955 when GE pioneered the first diamond reactor. And this was based on a high temperature, high pressure method where we had these giant diamond reactors that were about 2 stories tall. It was a novel concept at first. We cycle forward to 2003, we have this new process called chemical vapor deposition, where we could literally grow diamond. We use either a hot filament or a microplasma technique, where we put a substrate inside of a reactor, and we're actually able to grow diamond on top of these things. As I mentioned, Argonne has been at the center of the more recent boom. It's, as Amanda mentioned, one of the 5 Department of Energy nano labs, but this is the nano lab with the expertise in carbon, right? Diamond, carbon nanotubes, and graphene. And in 2003, they actually pioneered work over there at Argonne for diamond thin film technology, where we're able to put diamond on silicon, making diamond more cost effective. And what we're able to see is that this polycrystalline and nanocrystalline diamond didn't really vary too much from single crystal in terms of its electronics capability. And that same year in 2003, Argonne actually spun out Advanced Diamond Technologies, which has been doing some really phenomenal work in the diamond industry, particularly in biomedical, electronics, and water purification. More recently, they've actually pioneered a very effective technology which helps clean up water supplies and fracking, which is useful. But in the context of this lecture, we're discussing semiconductor applications. So if diamond is so great, where are all the diamond electronics? In 2003, the same year of that Wired magazine article I'd shown, the Department of Energy conducted a study on all wide bandgap semiconductor materials, which includes diamond, gallium nitride, gallium arsenide, in addition to some others. And while they concluded that diamond showed the best theoretical performance, there are certain processing problems that have not yet been resolved. It's a harder material, it needs even higher temperatures for processing, eerily similar to silicon, right? If we look to the leader in the semiconductor world, Intel, which has the largest market share, they concluded that diamond represents a seismic shift away in semiconductors. It takes about 10 years to evaluate a new material, and we have a lot of investment in silicon. They're not about to change that. So if we see that technology progresses in what's called a technology hype cycle, and we treat that 1955 as the technology trigger and 2003 as the peak of inflated expectations, what's the trough of disillusionment? What do we need to move this forward? Well, we need 2 things. We need to be able to put diamond down cost effectively at lower temperatures so we can integrate it with silicon so that investment isn't lost. And we also need to be able to make diamond conduct similarly to silicon, at least better than silicon, right? So we want to say, same or cheaper cost and maybe 10 to 100 times the performance. So I like to say that hindsight is 20/20, and since Intel said it takes about 10 years to evaluate a new material, here we are 10 years later. So previously in N-type doping, there was lots of problems in incorporating these atoms into the diamond structure. We would see that there would be crystallographic damage, where you could see via the scanning electron microscope image of a single crystal diamond, there are these pits in there. And if we think about this, an electron getting from point A to point B going across this pit gets scattered. And as we know, conductivity is directly proportional to how fast we can move these electrons and how many electrons are available for conduction. So if we think about it analogously, it's like driving on Lakeshore Drive with all the potholes versus driving on I-94 where we could really take off. So more recently, our work at CNM, we were able to show, using a new doping technique, we can use that same single crystal diamond, and under the same magnification, we could see that there's no more pitting. So how were we able to accomplish that? So initially, we had pioneered our R&D capabilities utilizing leading university nanofabs, such as Stanford's nanofab facility. But earlier last year, we began to collaborate with the Center for Nanoscale Materials, and particularly with Dr. Ani Sumant, to characterize the ACON materials. And shortly thereafter, we combined the ACON N-type process with a really neat technology developed at Argonne, the ability to deposit diamond at very low temperatures, approximately 400 degrees C. And this is important because now we can put diamond directly on silicon without destroying the underlying circuitry. Very shortly thereafter, we began developing this technology cooperatively to really bring this about into the market. And very shortly thereafter that, we won the 2013 R&D 100 award for it because of its magnitude and the long-standing issues in diamond. Here we can see on the right, via the atomic force microscope image, that at the nanoscale, there's no more of these pits. Rather, we have these protruding aggregates. So it really didn't affect adversely the electronic performance of this diamond material. And why was it such a breakthrough? Well, we dubbed it the Mirage Diamond Platform for several reasons. One, diamond is naturally an insulator, so it's almost a mirage that it's conducting at this point. But in combining these two things, we were able to have a new platform that really enables a diamond-based semiconductor industry, where rather than having this large two-story reactor, at CNM, they have a Lambda plasma-based system, which fits easily, as you can see, in one room. It's fully automated, and it really enables the capability for diamond-based electronics, where instead of using very high pressure and very high temperatures, we're able to use low temperatures and crack methane via this microwave plasma process. So we're able to take this CMOS-compatible diamond, we're able to make semiconductor-based devices out of it. How does that compare to what's previously been done, both the state-of-the-art in diamond and the state-of-the-art in silicon? Well, when we fabricated these pin diodes to comparatively demonstrate, we were able to see that some very fascinating things. From an electrical perspective, we're able to see, compared to the state-of-the-art in single crystal diamond, we can put about 200 times the amount of current through that same material. And when we compare that to the silicon-based devices, we can put about 1,000,000 times higher current through the same amount of material. What we actually noticed, though, from an economic standpoint, was we can use approximately 850 times thinner layers of diamond to accomplish that function, and approximately 1,000 times thinner material than the silicon counterpart. So for the first time in diamond, we actually have a cost-effective way of manufacturing these diamond materials. We're able to marry it with the silicon platform, so it's not just a seismic shift away, and we're able to actually go about a much broader market of applications. So, as I mentioned, we made these pin diodes, but really to go after the entire semiconductor market, you also have to make transistors, which we've been successfully able to fabricate. But in combining these two things, we're able to make a lot of complete systems that can address a lot of emerging and critical markets, for everything from faster supercomputers to satellite and telecom to aerospace. If we take a diode and a transistor and we combine them, we now have an inverter that enables hybrid electronic vehicles. If we need diamond to do things like be able to have increased signal capability at great distances, we can now incorporate them in aerospace and avionics systems. So really, it's addressing the needs of the current market while enabling future-based devices. Actually, I was prepared for a 15-minute talk, so I'm going to cut it short here. But I'd like to thank you for your attention. And I'd also like to acknowledge the CNM facility. Everything that you've seen in this PowerPoint was derived from there. We've worked with, as I mentioned, with Dr. Ani Sumant and the broader CNM community. Thank you very much. Yes. So the question was how close we are to commercializing this process. And it's interesting from a business perspective. we really don't believe that we can compete with an Intel or the like, but we believe that we can enable Intel and the like to do certain things. So we actually have a mixed-use philosophy where we're licensing to captive foundries, and we're also going about developing these devices. So actually, we've had our first customer this year. And we're also negotiating at a very high level some exclusive licensing. And we're also talking with very large concerns to develop joint ventures to collaboratively go about this. So I would say that I would expect over the next 18 to 24 months some very key announcements to that effect. Thank you. So the question was if the mayor of Chicago had approached us for a current work effort. Actually, we haven't been approached by the mayor, but last June, as a part of the National User Facility Organization, we gave a technology demonstration to members of Congress. So actually, they were very, very well received in terms of the technology. So the question was if we have a lot of competition from other scientists trying to replicate this work. And it's interesting, we don't really have competition from the semiconductor respect. We're actually unique in that not a lot of other diamond-based companies are working on N-type diamond or have had success with N-type diamond. But from a thermal management standpoint, absolutely. And especially over the last 12 months, a lot of the diamond world and some of the wide bandgap semiconductors have specifically turned their efforts to thermal management, realizing that this is going to become a major issue. And actually, independent analyst firm Yole Development recently did a study on diamond-based technology. And what they found was there's not really expected to be new entrants into the marketplace, but rather this would start to heat up over the next few years. And by 2020, we would see an actual diamond-based semiconductor market. So the question was if there are other materials being looked into for the same purpose. It's interesting. Other carbon materials are being looked at for similar purposing. So yes, graphene obviously has received a lot of attention, winning the Nobel Prize in 2011. But graphene is interesting because it's not a really good chip scale material because you can't turn it on and off, and there's not really a gap associated with it. But rather, people are looking into incorporating these materials, graphene on diamond, carbon nanotubes interweaved. So not so much competition, but rather complementary aspects to it. But what I really like about working in the nano diamond space is we're able to incorporate nano diamond onto other materials. One thing that was published with respect to the argon technology was the CMOS compatibility of diamond, for the first time being able to put nano diamond on gallium nitride without any interfacing material. Because the temperature is so low, typically when you put down diamond and gallium nitride, you have to have very large or very high temperatures. This causes the nitrogen atoms to diffuse into the diamond layer. But at 400 degrees C, we don't see that diffusion. So now for things like optoelectronic applications where gallium nitride is very important, we're able to see diamond complement that material. And actually we have thermally efficient LED devices where droopage is a major issue in optoelectronics. So the question was, they expect that diamonds are a very expensive process to use, and is, so if you could repeat the last part of the question. Sure. Well, so we realized that single crystal diamond is very expensive, right? And it's not only expensive from a material standpoint because it's just methane gas. Methane is one of the most abundant molecules in the universe. It's rather that in order to produce thick film diamond, it takes a long time in these reactors, weeks and weeks and weeks, right? But we're dealing with nano diamond where we can have microns per hour. And because we're dealing with like a half a micron in these materials, there's actually a quick throughput, right? But to address your second point about not wanting to give your fiance a transistor, it's interesting because in China and India, there are a lot of more diamond reactors coming online, and I'd expect to see in the next 12 months just flooding of these synthetic diamonds. So do check out what you're buying in terms of diamond.
That's a very good question. I will. So the question was whether, for all the years, long years, I've spent working on nanomaterials, whether we're still surprised by the way materials behave at the nanoscale versus how they behave in the bulk. And the answer is absolutely yes, every time. I mean, it really is still fascinating. You take a material you think you know very well, titanium dioxide. You know, I showed its application in nano batteries. I showed how you can use it in sunscreen. It also actually has applications in artificial photosynthesis. It's an extraordinary material. It's a semiconductor as well. So there are a lot, and it turns out to be very good for catalysis if you can make it in with the right crystal structure. So I think that's one of the reasons why we really put computer simulations and predictions together with the experiment, because sometimes, you know, we could look at thousands of different materials, and we wouldn't know quite which one to go after, but we can very quickly do those simulations in a computer and home in on what we would like the properties to be. Then we have to try and grow it and produce it, and that may be a difficult thing to do. But yeah, I'm constantly surprised by the way the materials behave, and sometimes actually by the way they don't behave. You know, we've predicted something, and then actually when you make it, it doesn't do what you expect. So the question was whether when we do computer predictions, whether we can actually use those and look at them to predict materials that will experimentally have the same properties, and also whether there is still room for development in the computation area. And the answer to both those questions is yes. It's very interesting. If we look at the work across nanotechnology globally, I would have said there's almost equally cases where a material's been predicted first and then grown experimentally, and the properties have been the same. Where experiment has come first, and then the input, the output from the experiment is the input to the model, and then where the two go hand in hand. So, for example, that work on the catalyst that I showed for transforming propane into propylene, that was all done in the computer first. And then once it had been done in the computer and the properties had been predicted for how the catalyst would behave, then it was made experimentally, and the theorists said, well, yes, we knew it was going to do that, you know, and we were just verifying that what they'd said was right. So that was certainly one case where theory led. I think one case where experiment led was with the hard drive materials, because theory had predicted how they should behave, but then it turned out to be incredibly difficult to make material that was perfect, because in theory, you know, you're going to grow perfect material. But in fact, it turned out that when you had all the defects in and rough interfaces and mixing at these interfaces and things, the material behaved even better. But theory hadn't been able to predict that because it was too difficult to do those calculations. So there's certainly always room for improvement in computation. And that's why argon, it has a blue gene P and now a blue gene Q, and we're going to even bigger and better computers because we need them. We actually need those very high computation speeds and those very large amounts of memory to do these ever more complicated predictions because we want to put in more realistic materials. Yeah, so the question is what kind of partnerships we would like to enter into at Argonne. So we would like to have, well, we would certainly like to increase the number of industrial users that we have coming in to all of the user facilities. I think industry, local industry in particular, is a user group that's underrepresented. And often that is because I think people find it difficult to find the information. We have a very good website. Matt Howard from Just Communications is here. We have a very good website, but you have to know what you're looking for. And I'm sure that for people in universities that's easier. They'll go and ask a professor and the professor will say, yeah, go and look on the Argonne website. But it's hard for companies. I'm sure Adam would be able to comment on that. And so we're looking for those kind of partnerships with industry. We're also looking for partnerships with universities, with local universities. We partner with other national labs. We partner in large conglomerates. So and we partner with institutions abroad. We would like to grow all our partnerships. I think science is not something that one can be done in isolation. I mentioned that we have to have all our groups internally with CNM working together. We have to work with everybody else outside. That's the way the new discoveries get made. So partnerships are absolutely critical with all different kinds of entities. Absolutely, thank you. So the question was, I showed one slide where I showed that the Department of Energy set up 5 nano centres. So the question was really what the strategy behind that was. So if you looked at a very sort of broad brush level, all of the 5 centres will have theory. They all make stuff, they look at stuff, and they predict stuff. They might all have very similar pieces of equipment. And that's because, of course, if you live in California, we can't fund people who come to work with us. We will give them access to the equipment and our wonderful people for free, but we don't pay for them to come and stay in Chicago. And so if you're in California, it makes more sense to go to Berkeley National Lab. And so there will be replication between the types of equipment that we have. However, what I would go on to say is that what really makes the centres different are the people that we employ. Because unlike a user facility in a university, which might have some technicians perhaps looking after it, we have world-leading scientists who are populating our nano centres. And so none of those 2 world-leading scientists are the same. They're very individual people. And so a lot of our users come to Argonne, as Adam, for example, to work with Anis Soumant because he's here at Argonne. And so by having those different populations of people are why we have users from California come to Illinois, and people from Northwestern might go to a center, say in Tennessee or at Brookhaven National Lab on Long Island. So the idea is that we would cover all the areas of nanoscience, but we would have specialization. And that allows a breadth that would not be possible if you had everybody in one center.
Are any of these electronic components employing nanoparticles affected by magnetic fields? And above and beyond that, would they be more susceptible to electromagnetic
I'll answer from the diamond perspective, actually. So the question was, at the nanoscale, are these materials more susceptible to magnetic fields and electromagnetic pulses? So it's actually quite interesting because, diamond is a very hard material naturally. But what we find is when we shrink it down to the nanoscale, it's actually a much higher pressure material, even as compared to single crystal. Because of these sp3 bonds in diamond are put together and they're randomly oriented, we find that the grains are actually able to do interesting things in response to pressure, which is what makes the nanodiamond such a useful material for things like microelectromechanical systems, MEMS and NEMS type applications. But from an electromagnetic standpoint, we don't see that same susceptibility or that same worry as compared to single crystal. But I'll let Amanda answer for the rest of nanomaterials. The rest of the universe.
Right, for the rest of the nano universe, I'll answer. It is a very good question. I think it very much depends on the material. We don't test them with electromagnetic pulses, and I would have to say, and when you talk about electric fields, I think, the kind of work that we're doing at the very small scale, as I said, we don't do a lot of device fabrication, so we will look at the much smaller level. We might look at a whole recording head, but we're not at the CNM going to be the people who develop the whole recording head and that whole system. And to be honest, I think that one has to consider the whole system in these cases, because often what's going to be important is perhaps the casing material, how you protect the device. You can protect some devices better from electromagnetic pulses. We certainly look at materials in extreme environments, and whether that be radiation hard or whether it be high temperature or pressure. We certainly are very interested in that, and we are doing experiments to look at it. I would have to say most of what we've looked at so far has been pressure, particularly from the point of view of things like batteries, because of just the size changes that you get. But I don't know, magnetic fields, very small nanoparticles are not ferromagnetic. They become super paramagnetic, in which case they don't respond except collectively to fields. And so they probably are less susceptible. We have to apply higher fields, for example, to reverse the magnetization as you go to very small particles. And of course, that's actually one problem that comes in with hard drives. As you make the bits smaller, it turns out that it becomes more difficult to write them. And so that's a problem that that's again a subject for a whole nother lecture, and I won't start on it because it's my area of research, so I'll bore everyone stupid.
I was fascinated to hear that in medieval stained glass, some of the colors are due to nanoparticles. I wonder if you could elaborate on that a little bit. Tell us a little bit more about that.
Sure. So the question was about the nanoparticles that color stained glass. So it turns out actually all the colors in stained glass come from nanoparticles. And it's really very interesting. It's actually, they change the wavelength of the light as it goes through. It's a non-linear optical effect. It's quite extraordinary, and I'm sure nobody in medieval times in Latin would have known to write non-linear optical effect, but that's what it is. So the light comes in, it interacts with the nanoparticle, and the nanoparticle then emits light that has a different wavelength. And I don't know how they came about this. I'm assuming that somebody melted gold together with the glass and mixed it up. And in doing that, they dispersed the gold into very small pieces, and that they then discovered gave a color. But it is fascinating, and the colors are so. You look at medieval glass even now; the colors are still so bright and so strong, and it's not. And of course, if it had been a paint, that probably would have flaked off. But it's actually built into the glass, so it isn't color that can come out. It is fascinating.
One more comment on that one. Who has an answer to question? Yeah.
Okay, so the question is asking about nanorobots. and whether there's any research going on at that at the nano centres. It depends slightly what you mean by a nanorobot. If you're thinking of the kind of thing that has been projected theoretically, where you could have a small entity that would go around inside your blood vessels and repair them, or do something like that, no, we aren't doing research on those. The nano centres are not. They don't have a remit to do medical research. We might work on nanomaterials that might ultimately have a medical application, but that medical application is going to be worked on by our collaborators or our users who come in from a medical centre somewhere. There's certainly work on looking at how you can attach antibodies or some other type of molecule on the outside of a nanoparticle, and you could perhaps send that round through the body. Nanoparticles are being looked at for drug delivery. I mean, just one example, you could attach a drug molecule onto a nanoparticle and then send it round through the body. I think the problem is at the nanoscale, I mean, to have something like a nanorobot, you have to power it. And so you've got to find some way that you would be able to power something at that scale. And that's, and also it has to have moving parts, and we can make some little things that will move together, but that's a very complicated sort of complex of different things that you have to put together. So we're not there just yet.